So now we want to finish the second section of Chapter 13 of Young and Freedman's University Physics on simple harmonic motion. We want to get some formulas developed on how to determine the displacement, how to determine the velocity, how to determine the acceleration, the phase angle, which we'll talk about in a second, the amplitude, these aspects of harmonic motion, for example, in a spring bouncing back and forth. We want to get some formulas on the table. This last part of the section, I divided it into another video because it's a little more complicated. It took 10 minutes to do the first part. We'll see how long it takes to do this one. So let's talk about displacement of, say, a glider or whatever something on a spring. Displacement is a function of time when it comes to simple harmonic motion. Okay, well here is the formula right here. Where did this formula come from? Well, if you remember in the previous video, and I can actually go back to the circle here. There it is. On this circle, we determined that if there were a kind of, if we think of the timing of this as a circle in radians, then the displacement along the diameter up here is going to be the cosine of this angle times the radius of the circle, which we might also now call the amplitude, the total amplitude. So a cosine theta, where theta is the kind of the phasor rotating, is going to give us the x along this diameter at any point. That's in the previous video if you want to go back and see it. But basically that's where this formula comes from. So a cosine of theta, what is theta? Well, theta is this angle on a hypothetical reference circle that we could equate to, say, a spring going back and forth. Well, what is theta? Well, theta is basically the number of radians. And how do you find the amount of radians? Well, if you take the angular velocity, which is radians per second, and you multiply it by the time, which is seconds, you end up with radians. So omega t is another way of saying theta. So a cosine theta, that's exactly what we had before. Where does this second letter, the phi, that's the letter phi or phi, I guess we'd probably say, where does the letter phi come from in this formula? Well, phi is something that there is called a phase angle. So if the spring starts at 0, then we would say that the phase angle is 0. But what if we're measuring the displacement from some other point, maybe where it's already stretched a little or compressed a little? That phi component basically allows us to start considering distance at some point other than the 0 point. But everything we've done so far has started with the 0 point, and so phi has been 0, which means that we've just been left with a cosine of omega t, which is a cosine of theta, which is a formula we had before. If you didn't understand any of that, hold on, don't worry. We'll understand enough to get through this by the time this video is over. So here's the explanation. I'm going to do it again because here's the actual words. The reason why this formula works is because x equals a, the amplitude, times the cosine of theta, which is basically on our hypothetical reference circle, this remember q that's going around the circle casts a shadow on the diameter that is the simple harmonic motion. So anyway, x equals a cosine of theta, and then we've introduced now the phase angle phi, just in case you haven't started with the spring at 0. Phase angle basically means where you start. We start this harmonic oscillator in progress. If you start it in progress rather than at 0, that's what that phase angle is for. Okay, so if x equals a cosine omega t plus phi, then we can now use a little calculus to come up with formulas for velocity and acceleration. Now, if you don't know calculus, just memorize the formulas. But basically, in calculus, the way that you take the derivative of a cosine, the derivative of a cosine is the sine of the thing plus the derivative of what's inside the cosine. So cosine becomes sine, and then we take the derivative of this let me see if I can get my cursor, this omega t plus phi, I take the derivative of that. Phi is a constant, derivative of a constant is 0. Omega t, the derivative of this with respect to t is just going to be omega, and so this omega comes out. And I'm sorry, I said it wrong. The derivative of the cosine of something is the negative sign of something times the derivative of the something. So the derivative of the cosine becomes negative sine. A is a constant, so it just stays in front. And then the derivative of this is omega. And then I'm left with the same thing inside. If you don't understand that, don't worry about it. You might review how to take the derivatives of transcendental functions or trig functions. But if in doubt, just memorize that this is the formula for the velocity of a harmonic oscillator. Okay, so to get the acceleration, we just take the derivative again, a dv dt, the second derivative of x, as it were. So the derivative of the sine is the cosine. So we're going to left with negative omega a cosine, and then we're going to multiply it by the derivative of what's inside the parentheses. Well, again, the derivative of phi is 0. The derivative of this is another omega, and so we're left with omega times omega, is omega squared, and then the derivative of the sine is the cosine, and blah. There you have it. Again, if you don't understand the calculus, just memorize the formulas. So we now have a formula for the displacement of a simple harmonic oscillator, for the velocity of a simple harmonic oscillator, and for the acceleration of a simple harmonic oscillator. Don't let the length of those formulas throw you off. Just plug in the values. Okay, so again, the phase angle. How do we solve for the phase angle? Well, if you follow Young and Freedman, the chapter section 2 there, they give an explanation, and it's not important, again, it's to know the explanation, just to know the formula, but let me kind of go over their explanation. So we know from this previous page that velocity equals negative omega times the amplitude times the sine of the phase angle plus, omega t. So we've got that formula, right? And we know also, remember, from the previous page, that x equals a cosine of theta. So now here's where somebody came up with something clever. If we divide the velocity by x, we end up with the negative omega a sine of phi on the top and the a cosine of phi on the bottom. I'm sorry, this shouldn't be a theta. This should be a phi. Anyway, sine divided by cosine is tangent, and so basically v over x equals negative omega tangent of phi. So now all I have to do is divide both sides by negative omega. That gives me tangent of phi equals velocity over negative velocity over omega x. Now I zap an arctangent, and I'm left with phi equals arctangent of negative v over omega x. That's the formula. If you didn't understand how we got the formula, don't worry about it. But the formula for the phase angle is the arctangent of the negative velocity divided by omega x. Okay, that gives us 4 important formulas in this last part of the section. We know how to do x, we know how to do v, we know how to do a, we know how to do phi, and now we want to find a formula for finding the amplitude. I've gone ahead and done what they kind of tell you how to do but don't do. So if x equals a cosine of phi, so then x squared equals a squared cosine squared phi. Fair enough. Don't know why I did it, but okay, I understand that. So, and we know that v is omega a sine of phi, right? So if we square it, v squared equals omega squared, amplitude squared, sine squared of phi. Now, if we add phi, if we add these both together, then, doing a little algebra, we end up with the amplitude squared times the cosine squared phi plus the sine squared of phi is going to equal x squared plus v squared over omega squared. Well, why did we do this? We did this because there's a trig formula. Cosine square x plus sine squared x equals 1, which means that whole part in parentheses over here on the left becomes 1, and we're left with a squared equals this. Take the square root, and we have this formula for the amplitude. The amplitude of something in simple harmonic motion is going to be the square root of the displacement squared plus the velocity squared divided by the angular frequency squared. Boy, this was some hard stuff, but I think it's understandable. But if in doubt, just memorize the formulas and apply them, and you'll be just fine.